Hello everyone. In this video we're going to take a look at some examples of free body diagrams. Okay, so the first example is person pushing on a wall. So here's a representation of that. You're standing on the wall, your arms, and we'll just put them acting on the same location. You're pushing on it, so your muscles are generating a force which is in contact with the wall. So if we choose as the free body diagram U, so the boundary is your body, including your hands, which is in contact with the wall. We've specified the free body by specifying the boundaries. Now what are the interactions with the world? So the rest of the world is the wall and the ground. So I think some fairly obvious ones are contact with your feet and the ground. You probably have some weight you want to represent. All right, so the force acting on the wall, let's take that as just being acting normal to the wall. Certainly, depending on the angle of your arms, it could be a force applied at an angle, but let's say that everything is aligned just so that it's perpendicular for simplicity. So there's an equal and opposite reaction from the wall pushing on you. You push on the wall, it pushes on you. So external to you is the wall's force. So I'm going to put that in another color, and I'll put that in force, wall. All right, anything else? Well, it depends what you're standing on, right? So if you push on the wall, you could slide away, as you can imagine if you were standing on, say, ice. But likely there's some kind of frictional force or something that's holding you possibly in place. So I'm going to draw a frictional force here on each of your feet. A simple frictional model, as was discussed earlier, is something that is parallel to the surface or perpendicular to the normal. And these go in the direction, opposite direction of motion when slipping. So if you were to slip and slide along the ground, which direction would you be going? You're pushing on the wall, so the action of the wall pushing on you is this way. You would then be moving to the right, so the friction is opposing you, that motion, so it is going to the left. Likewise, depending on how you would model or take in consideration your hand, you may want to have some kind of friction force acting here on the wall. In these simple frictional models, that may be something that needs to be applied. Anything else? We're going to neglect other forces that we think, gravitational pull from large bodies. Any moments to apply? In this case, it doesn't look like there are any moments. The wall is not twisting or causing your body to rotate in any way. So we just have a series of forces being applied to the free body diagram of your body. Okay, in the second example, let's consider a wall. Here's a side view, and I'll just take a simple cantilever beam. So think of a diving board, say. Let me just draw a sort of explode angle view here. So you've got a diving board built into the wall. Okay, and somebody's going to come and stand on it. So your engineering question may be, if we don't want it to deflect, or we don't want it to deflect very much, how thick should we make the diving board, or what material? So we have some question about the deformation of the board. So we're going to make a free body diagram that describes what the board is doing. So if we take the side view, let's draw the board here. And we're assuming that the board is rigid, it doesn't deform very much. We can represent the contact with the person. It looks like they're touching the board in two spaces. Perhaps we do not need this detail. We'll just lump those using an equivalent force, the force of the person on the beam. This is built into the wall, right? So you have to assume, you need to decide, or this is part of your model, what the wall is doing to the board. How is it holding it in place? Say you wanted you use the fixed condition. So fixed meaning, this is a sort of word for meaning no rotation, no translation. So this board is stuck into the wall. It's not going to move up and down. It's not going to translate anywhere. And it's not going to rotate. It's not going to bend. It's going to stay essentially straight, sticking out of the wall. In that case, what do we have to apply from the wall to the board? Sounds like we have to get a force. Possibly we need a force in this direction to keep it from pulling out of the board. And if we want to keep it from rotating downwards, it seems like we have to have a moment. So if we call this contact point A, say, so we have to denote a moment with respect to a point, and there's a moment being applied by the wall. So the wall is doing three things. Well, it has three interactions. We're describing the wall interaction with three vectors, two forces, plus one moment. That's the wall interaction, so wall interaction. Anything else that we missed? If this is a very heavy board, perhaps the weight of the board is important. We may want to describe that with a distributed force. We could lump that together at some point as an equivalent force, or perhaps we just neglect it altogether. So in this case, we may have something that looks like this. Call that F2 and this F1. Or if we could possibly neglect the weight. And that would be an engineering decision that you would have to make for your model.